Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today, it is the 13th lecture of this course, and the topic is wave equation. First, I will give the learning objective. At the end of this lecture, the student will understand the general form of the wave equation as given. In this lecture, we will see the derivations of such equation. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. In this lecture, some of the illustrations are taken from this book. As we have discussed in the previous lecture, that when a wave passes through a string, each element of the string moves perpendicular to the direction of propagation. If you remember, we have a string, and over that string, a wave is traveling towards the positive x direction, and we have marked different elements on that string such that each element is just moving up and down relative to the direction of propagation. That is, if we just concentrate on this single element through that slit, so when the wave passes through that string, the element A, say, just moving up and down, that is, it is moving along the y direction through that equilibrium point. So we will apply the Newton's second law on this single element, for example, and then we will generalize it, and then to derive an equation of motion. So for that, by applying Newton's second law to this element's motion, we can derive a general differential equation that is known as the wave equation, and that governs the traveling wave of any type. So for that, we need to just consider this small element and applying the Newton second law. So let's see, we just consider this portion. So for that, we need to consider that same element of length L that is moving along that y direction with acceleration ay because of some forces on this side of that element of the string and also on that side. So the net force will be the difference of the two. The length of that element is, say, L, and that is equal to dx if we just make our measurement along this x coordinate in terms of length. So that is moving, that element is moving along y. That force we have discussed in the previous lecture, that is tension in the string. So the net force on that element is the difference between the vertical component. If you remember, we have seen that the horizontal component just cancels out, not contributing towards the motion along the transverse direction. So if we just consider this one force in this figure, so that F2 force is having F2x component and then F2y component, and similarly for the first force, let's say on this end the force is F1 and on that side it is F2. So this F1 can also be decomposed into transverse and the tangential component, so that we will be having f1y, and then we have f2 f1x. So in the same way as we have shown for the f2 force, so that acceleration along the y-axis will be due to the net force along that coordinate. So that will be the f2y minus f1y equal to ma, such that the mass of this element is dm, a small element having small mass dm and having acceleration ay. Now this dm can be expressed as dm equal to mu times L, if you just remember the last few lecture, where this mu is the linear mass density, which is defined as mass per unit length, and such that this mass is dm over L, the length of that element, and if you remember, this L is just approximately equal to the dx, so that this small mass dm, which represent the mass of this small element, can be expressed as mu times dx. Now the acceleration can be described, this is along the y coordinate, so that will be d square y over dt square. So we have just find out the measurable quantities in this force equation, which is Newton's second law. Now on the next slide we will see how we can find out these two components of the force, the F1y and F2y. So the same figure over which we have started with this Newton's second law, and that is F2y minus F1y will be equal to the net force equal to ma, where m is the mass, and in this case this is dm, and ay is the transverse acceleration. As we have discussed, this dm can be expressed mu times dx and the acceleration can be expressed as dy d square y over dt square. So now this force f2y over f2x can be expressed or can be related to the slope, say s2 on this figure. Similarly for this one, but we are discussing the one side, and then we will assume a similar solution for the second one. So this can be related to the slope, which is that tangent line s2, such that the magnitude of this force, which is f2, which we have written in component here, so that can be expressed as f2x square plus f2y square under the root. So that is the magnitude of the force f2. Now as we have discussed previously, that force is the tension in the string, so that f2 can be expressed as tau, which represent the tension in the string, and that will be equal to the same expression. Now we are assuming small amplitude waves, so that assuming that the element is only slightly tilted, so that this f2, the vertical component, is smaller compared to the horizontal component, that is this portion, this is small compared to this one. So under this condition, the expression for the tension will be equal to tau is equal to f2x, so that this is small compared to that. So the tension will be equal to the f2x on that side. So if we just put that f2x equal to the tension in the first expression, that is instead of writing f2x, we can write tau, so that this F2y will be equal to tau times the the S2 vector. Now, similar analysis can be done on this side of the string, so that decomposing this F1 into F1x and F1y and finding out that the first force in the y direction is equal to the tension times the S1 vector, which represent that tangent line. Now, once we have in this f is equal to ma expression, we have dm is mu times dx. We have the acceleration along the y coordinate, that is d square y over dt square. We have the force along that y coordinate on this side and also the other by these two expressions. So now we can put all these parameters in this Newton second law expression, so that instead of writing F2y, we can write tension times S2 and F1y tension times S1. Instead of the dm, the mass, mu times dx, and instead of the acceleration, we can write d square y over dt square. Now, taking this tension common across this equation, so that on this side this tau will appear here, and instead of this dx, that will come here, so that this S2 minus S1 can be expressed as ds. Now, and this S can be described as dy over dx on this figure. This is the y coordinate and this is the x coordinate, so that this slope will be dx over dy over dx. Now, writing this S2 minus S1 as ds, as I told you, and then instead of this S, we can write dy over dx, so that we will be having d square y over dx square, just to complete it here, so that we will be left with this general form. Now, we know that the velocity or the speed of the wave along the string can be expressed as under the root tension over the mass per unit length, or the inertia factor, so that this mu over tau can be expressed as 1 over v square, so that this expression takes the general form of this wave equation, which is not limited only to the wave traveling along a string. Now, this equation can be used for any wave mechanism, such that this v will represent the velocity of that particular wave in that particular medium. Now, as I told you, that this is general differential equation that governs the travel of a wave of all time. Now, you need to solve these three problems, which is based on the wave equation. The function is given, all the informations are there. This is the ym, this is the k, this is the omega, and then you need to find out, for example, in the first question, you need to find out the speed of that wave. So remember, you need to use the wave equation. So use the wave equation means that you need to differentiate this function twice with respect to x, and then you need to differentiate twice this function with respect to time, and then you need to equate them such that 1 over v square will be on one side, and from that expression you will find out the speed will be equal to omega over k. And here you have omega and you have k, and you need to just go through the wave equation. Similarly with the other two problems. So with this, I need to thank you for your time.